Hello everyone, so in this particular video we will be coding the transformer encoder model from scratch. So let's start with the import. So we are going to import torch dot nn as nn, and then finally we will also need torch.nn.functional as f. Okay, we'll also need math for the log or maybe for other things for the sqrt. Okay, once that is done we will be defining certain functions. So we will need first certain classes, not functions. So we will need self attention. Okay, so this is one module that is very much required and it will inherit from nn.module. Then we'll have to define the function, we'll have to initialize it, we're going to say self, and we will here only need d of model, which is the dimensionality of the model or the embedding dimension. After that you will have to define the super, and you're going to say self attention. So I'm going to just copy it from here and then going to say self again and then init. Okay, now we have to define certain things. First, d of model itself. So we're going to say d of model, d model is nothing but d model. Okay, so we are just saving it over here. Okay, after that we need three matrices, if you remember, query, key and value. So I'm going to say nn.linear, self.query is nn.linear, and let's keep it very simple. Let's do single self attention. Okay, let's not complicate it a lot. So let's say d dot model, and we are going to say self dot key over here, and I'm going to say nn dot linear again, then d of model again one more time over here, d of model, fine, d of model comma d of model. So I hope you already understand, you know, how nn dot linear and other things work. Okay, so self dot value is nn dot linear, and then d of model comma d of model. Okay, so these are the initializations that we are going to have. Let's write the function definition or def forward. So I'm going to say forward, and let's have self comma x, which is the input x. Okay, so first we'll calculate the key, query and value. So we will say q equal to query into x. So k is key is key. So capital K is the key, and you get it by self dot key, not just query, self dot query. Again here also self dot key. Finally, if you also need the value, which we do need, we are going to say self dot value and then pass in x. Okay, once you do that, you need to find the scores. So for the scores, I'm going to say torch.matmul. So if you remember the scores, let me just go and explain to you. So you already have the query, you have the key, and you have the value. Okay, you have already these things. So scores, if you remember, it is going to be q into k to the power transpose. Okay, and then you divide it by the embedding dimension or d of model, root of d of model. Okay, very simple. We have already seen all of this in our theory videos. So I'm going to say q comma t k of transpose. Then how we are going to transpose? We are going to transpose the last two dimensions. So we are going to say -2 dot -1. After that, once the transpose has been done, you need to divide this entire thing by torch.sqrt. So you might also use math.sqrt. I'm using self.sqrt, torch.sqrt, and then you divide it by the root of the dimensionality, which is d model, self.d model. Okay, once that is done, after that you need the attention weights. So the attention weights, if you remember, attention weights is nothing but you will have to pass it through the softmax function. So f dot softmax, and then you pass the scores, and then you pass the dimension as -1. Okay, so if you see, the scores was over here, but attention weights, for the attention weights, what you had to do, you had to take the softmax of the scores that you had found in this step, scores, scores, and then use you have to use the dimension dim equal to -1, which is the row dimension. Okay, so if you add all the values along the row, you'll get 1. That was the idea. That was the idea basically. Okay, so once you do that, you need to find the output is going to be torch.matmul, and you are going to have attention weights that we have found in the last step over here, attention weights that we have found over here, comma capital B. get some space over here. So this is done. Now over here, finally we will return our output and attention weights. Okay, so we are going to have shift and enter over here. So finally we have that. We also need the to see your so if you remember the architecture, let me just show it to you one more time. The architecture was something like this. Okay, so here you had your self attention. Here you had your add and normalization. Then you had over here again the feed forward neural network. Again you had your add and norm. Okay, and you had over here the skip connections. Okay, so skip connection was there. Again here some skip connection was there. Okay, so these are the two things. So skip connections when I'll be defining the block, that time we will be having it. Right now let me just go and define the feed forward neural network. So feed forward, and we are going to inherit from an module. Again we'll have def init. Okay, sorry, we'll have def init, and we're going to say self, again d model, and f dimension. Now in the theory we only used one feed forward neural network, but here you can have multiple. Okay, then we have to pass in the layers and in dot linear, and we are going to define an d dot model comma f dimension. Same thing for L2, so we're going to have self L2 and in dot linear. Finally d dot model comma ff dim comma d of model. Okay, once that is done, let's define the dim not fine. After that we have to define the forward function. Okay, so we are going to say self dot forward self comma x, and then we just return everything. Okay, so first what we'll do is we'll pass the entire linear thing. We'll pass the x, which is the input, through the first layer. Okay, so we're going to say self dot L1. After that we need to apply the relu function, so I'm going to say f dot relu. After that we'll pass it through the second layer, which is just going to be self dot L2. Okay, so we do this and then pass self to say shift and enter. So having done that, we have basically done two things. Okay, we have defined our feed forward neural network, and we have also defined our self attention. Now if you know, we just need to combine it using a block. So I'm going to have another function, so not function, I'm going to have another to say class, and we already have this encoder block. Okay, so once that is done, we are going to have an dot module. So this is what we're going to define. Okay, transformer encoder block, which is this entire block thing. Okay, then what we're going to have is we are going to have def init self, and we are going to have a couple of things over here. We're going to have d of model, then you have ff of dim, and then you are going to have also dropout. Okay, dropout we will be needing for our outputs, so let's keep it as 0.1. Let's define our self. First we'll have the super function, super definition. So transformer encoder block, and we are going to pass in self and then init. Okay, so let's keep it till there. After that we'll have our first self attention thing that we have already defined, self attention. Okay, then we are going to just instantiate the object. So we will say self attention, we needed to pass d of model, that's it. Okay, then we'll also need the ffn, that is the fully forward feed forward network. So we're going to say feed forward, we're going to say feed forward, and here what we can do is we can just have the outputs over here. Okay, because this will give us two things, so let's just keep it till output feed forward. Okay, so let's keep it over here and then give it d model, and we also need to give the ff dim. Okay, feed forward dimension, so basically the hidden dimension, but let's just call it ff dim. Okay, then we also have to have two norms, so nn dot layer norm, and we have to pass in the d of model. Same thing, let's just copy paste, and over here you'll have the same thing. Instead in norm 1 you're going to have norm 2, and finally you'll also need a dropout. So I'm going to say self dot dropout is equals to nn dot dropout, and we are going to pass in the dropout, which is going to be a probability of 0.1, which we have already given. If you want to override this, you can definitely do that. Okay, then we are going to have our forward forward function, we are going to say self.x. Okay, so once you do that, you're going to basically give your attention weights, attention output. So I'm going to say attention out. Okay, so we're going to have self.attention, self.self-attention, self-attention that we have already defined over here, self-attention, and we are going to pass as x. So self-attention is already there, we are going to pass as x. So this will go to our forward function over here. This forward function is there, right? In the self-attention over here, you can see self-attention, there is a forward function. This is what will be called, okay, here. After that, once you are done with that, we are going to basically add. So this was self-attention, now we have add plus norm, right? So we are going to say add, which is self dot dropout. Whatever is the output of this, we are going to use a dropout, okay, and then add the original input, which is just x. Okay, once you are done with that, you can say x is equals to self dot norm1 and then pass an x. So this is your first part, this is your this part. Where is it? This is your this part. This part has been completed till now. Let's go for the second part. Okay, so once that is there, then ffn output, ffn output is self dot ffn and then you pass in the x. Once you do that, you say x plus self dot drop out. Okay, and then you pass in ffn out. So whatever is the output from here, whatever is the output from the feed forward, you pass it over here and then you add the initial, which was this over here, x over here. Okay, right? So ffn out, this one is there. After that, you just do self dot let's say norm2, and then what you do over here is you pass in again x. Finally, you just return it. So okay, torch in the module is not there, capital M, not small m, whatever. So these type of typos happen. So you can see this is the entire code. Okay, not a big issue. You can definitely use this particular code for your, let's say, transformer encoder block. Okay, transformer encoder block, you can say TE, let's just call it TE. Okay, let's call it TE. And what do we need to pass? We need to pass certain things. We need to pass D model 512. Let's pass ffdim, let's say 1024. Okay, let's pass this over here. And you cannot have an init function. What does that mean? Okay, there's one thing that I forgot over here. I have to also write super feed forward. Okay, forward, and you're gonna pass in the self and then init. Okay, so these small little typos happens all the time, and you can see this finally ran, thank god. Then what you need is te and then pass in some random values, so rand n, and let's pass in, let's say 16 comma 10 comma 512, and let's just print the shape of it. Okay, let's not print the entire thing. Okay, so one more important thing that I forgot over here, instead of torch.sqrt, because this again needed to be an tensor, I had to write math.sqrt, which I thought could have been used, we could have written torch.sqrt, but again, since this is a simple number, it's an integer, we have to use math.sqrt. Finally, if you run everything, it works, you can see. Okay, so the code will be in the description. If you have any doubt, please write in the comment section. If you like the video, please like the video. Thank you very much and bye.